For more than a century, physicists have been fascinated by dark holes, with the idea gaining momentum around 1916. These astronomical oddities are among the most captivating and perplexing phenomena we know, sitting at the intersection of immense gravitational forces and a peculiar invisibility to our understanding. A dark hole, potentially weighing as much as 2 to 4 times the mass of our Sun, remains a mysterious presence in the universe. Despite decades of intense research, our comprehension has expanded from virtually no knowledge to piecing together more details, with even more discoveries being made recently. A breakthrough by M. Yakubu has uncovered surprising insights about the interior of dark holes, potentially challenging long-held assumptions and offering new perspectives on the nature of these celestial bodies. This new information opens doors to deeper investigations into what may have been overlooked until now. Dark holes exert such massive gravitational forces that anything entering their space is drawn into a singularity, a point where the laws of physics, as we know them, cease to function. In simpler terms, dark holes resemble enormous vacuum cleaners, pulling everything into them. One of the most startling aspects of studying dark holes is that if someone were to fall into one, they would gradually stretch and be torn apart by intense gravitational forces before reaching total obliteration. Despite their presence across the universe, the nearest dark hole is nearly 500 light-years away, yet its proximity still raises genuine concerns. In 2021, scientists achieved a historic milestone by capturing the first clear image of a dark hole, the M87 dark hole. This achievement was the result of numerous nights spent capturing and aligning images to create a single, coherent picture. As more data was collected, researchers identified that dark holes consist of 3 distinct layers, contrary to the common misconception that they are simply vast voids. The first of these layers is the event horizon, marking the point beyond which nothing can escape. Once something crosses this boundary, it is inevitably drawn toward the dark hole. The second layer, known as the photon sphere, is where light itself becomes trapped, unable to escape due to the powerful gravitational forces at play. Finally, there is the singularity, where all matter is compressed into an infinitely small point, causing the very fabric of reality to collapse, and known laws of physics break down. Each dark hole is unique in its own way. While they follow the general 3-layer structure, their behavior can vary significantly, making them particularly challenging to study. Traditional scientific methods do not apply to the exploration of dark holes, forcing researchers to investigate these anomalies through indirect means, such as observing the radiation they emit or analyzing the gas and dust swirling around them. Sending a probe directly into a dark hole is futile, as anything crossing the event horizon is inevitably pulled toward the singularity and crushed into nothingness. This unavoidable fate means that billions of dollars cannot be spent on probes that would be destroyed before providing any valuable data. As a result, scientists are left to study dark holes in 2 dimensions despite their 3-dimensional singularity. The origins of dark holes suggest that they may form when massive stars collapse in on themselves. As a star burns its fuel, it can no longer generate enough energy to counteract the inward pull of gravity, leading to its eventual collapse into a dark hole. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. To further understand the nature of dark holes, NASA scientists turned their attention to the center of the universe, particularly the M87 galaxy. There, they observed a powerful vortex of hydrogen gas spinning at staggering speeds of 1.2 million miles per hour. The centrifugal force should have caused this gas to disperse, yet it remained intact, suggesting the presence of a massive object at the center, likely a dark hole. This object is believed to weigh up to 3 billion times the mass of our Sun. Another significant theory was proposed in 1963 by New Zealand mathematician Roy Kerr, who used Einstein's equations to describe the behavior of rotating dark holes. He argued that rather than collapsing into a point as previously thought, a rotating dark hole forms a thin, ring-like structure known as the ergosphere. This rotating ring of matter is crucial to understanding the breakdown of physical laws in the vicinity of dark holes. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could provide a shortcut through space-time, connecting distant regions of the universe or even parallel universes. To grasp the concept of a wormhole, It is essential to understand the nature of spacetime as described in Einstein's theory. Spacetime is a four-dimensional fabric that is warped by objects with mass, creating gravitational fields that influence the movement of other objects. Imagine spacetime as a piece of paper. If you fold the paper, you create a shortcut between 2 points. This shortcut is the essence of a wormhole, a passage through spacetime that could link distant locations almost instantaneously. Although wormholes remain a theoretical concept with no direct evidence of their existence, they are a natural consequence of general relativity. However, wormholes are inherently unstable, meaning they would collapse quickly if created. Despite this, the idea of a wormhole as a potential gateway to different parts of the universe or even different points in time has captivated physicists for decades. One specific type of wormhole, known as the Kerr wormhole, has been a subject of interest. Named after Kerr, this hypothetical wormhole could theoretically connect two distant points in spacetime, possibly even linking different universes or timelines. While using wormholes for interstellar or time travel is an exciting prospect, there are significant challenges to overcome. For one, wormholes are predicted to be unstable, and the extreme radiation and forces surrounding them would make it nearly impossible to traverse them safely. Critics argue that Einstein's equations, while useful for understanding gravity, do not account for the quantum forces that govern radiation and subatomic particles. To truly understand dark holes and wormholes, a new theory is needed, one that unifies gravity with quantum mechanics. This theory, often referred to as the theory of everything, has been pursued by many physicists, including renowned scientist Michio Kaku, for decades. One promising candidate for this theory is superstring theory, which suggests that subatomic particles are actually tiny vibrating strings. The theory proposes that these strings form the fabric of the universe, explaining not only gravity but also the phenomena surrounding dark holes and wormholes. However, superstring theory also requires the existence of extra dimensions of spacetime that are so small they are impossible to detect with current technology. Despite the challenges, the pursuit of understanding dark holes, wormholes, and the fabric of spacetime continues to captivate scientists, offering the potential for groundbreaking discoveries that could reshape our understanding of the universe. Moving forward, the search for superstring theory and other theories that aim to unify the forces of nature remains an ongoing challenge, but it holds the promise of unlocking new insights into the very nature of reality itself. These theories suggest that the universe consists of more than the familiar 3 dimensions of space and 1 of time. In fact, they propose that additional dimensions exist, but they are so minute and compact that we cannot observe them directly with current technology. However, their existence could provide the key to understanding phenomena like dark holes, wormholes, and the deepest mysteries of the universe. Superstring theory offers a fascinating picture of the universe, suggesting that all matter and forces are manifestations of tiny vibrating strings. These strings can vibrate at different frequencies, with each vibration corresponding to a different particle. Just as a guitar string can produce different musical notes based on how it vibrates, the fundamental particles of nature could correspond to different vibrational patterns of superstrings. If proven, this theory would not only provide a unified explanation for the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new ways of understanding the structure of the universe. The study of dark holes is not just about understanding these strange objects in isolation. It is also about comprehending the fundamental workings of the universe. Dark holes are central to our understanding of spacetime, gravity, and the very nature of reality. By studying them, we are not only learning more about these objects themselves, but also about the laws that govern the universe at its most extreme. Whether they are gateways to other dimensions, as some theorists believe, or whether they hold the key to understanding the deepest secrets of spacetime, dark holes remain a crucial area of study. As our tools and theories evolve, so too will our understanding of these enigmatic objects. Avenue of exploration in the study of dark holes is their relationship with time itself. According to Einstein's theory of general relativity, time is not a fixed, universal constant but rather a flexible dimension that can be stretched or compressed by gravity. The immense gravitational pull of a dark hole warps spacetime so drastically that time slows down significantly for an observer approaching its event horizon. This phenomenon, known as gravitational time dilation, means that someone falling into a dark hole would experience time at a much slower rate compared to an observer far away. In theory, if a person could somehow escape after spending time near a dark hole, they might return to find that many more years had passed for those who remained outside. This idea has profound implications for the nature of time travel. Some physicists speculate that the extreme warping of space-time around a dark hole could create a natural time machine, allowing for travel into the future. However, traveling back in time remains a much greater challenge, as it would require conditions that are not currently known to exist in the universe. Despite this, the concept of time loops, where time behaves in a circular or repeating manner near certain cosmic structures, continues to be explored in theoretical physics. Another key mystery surrounding dark holes is their role in the evolution of galaxies. Observations suggest that supermassive dark holes exist at the centers of most galaxies, including our own Milky Way. These dark holes, millions or even billions of times the mass of the Sun, appear to influence the formation and structure of galaxies. Scientists believe that dark holes may have played a crucial role in the early universe, acting as anchors around which galaxies formed. The interaction between dark holes and surrounding matter can create powerful jets of energy, influencing star formation and shaping the cosmic landscape. One of the most intriguing questions about dark holes is whether they truly destroy everything that falls into them. According to classical physics, any information about an object that enters a dark hole is lost forever. However, this idea conflicts with the principles of quantum mechanics, which state that information cannot be destroyed. This contradiction is known as the information paradox, and resolving it is one of the biggest challenges in modern physics. Some researchers propose that information might be preserved in a highly scrambled form on the event horizon, while others suggest that it could be released in a different form through a process called Hawking radiation. Hawking radiation, proposed by physicist Stephen Hawking in 1974, suggests that dark holes are not entirely black but slowly emit radiation over time. This process, caused by quantum effects near the event horizon, means that dark holes can gradually lose mass and eventually evaporate. If true, this would imply that,